Welcome, this is Information Service Engineering, lecture number 5, Basic Machine Learning. 5.7, Deep Learning. We will talk now in the end of the lecture about the most popular field of machine learning, which is deep learning. As you might remember from the very first lecture inside that course on neural networks and machine learning, deep learning and neural networks are inspired by biology. This means they reflect somehow the basic building blocks and mechanisms that also work inside of our brains. And in our brain, the basic building block of our intelligence is the so-called neuron. And as you see here, the neurons, they encode everything with electrical pulses. So the majority of neurons encode the outputs or activations as a series of brief electrical pulses. And in our brain, we have about 100 billion of these neurons. And of course, they are connected with each other via so-called synapses, and there are about 100 trillion of these synapses. So with our artificial neural networks, we are far from these numbers, but nevertheless, we try somehow to adapt. So how does it work? Let's just have a brief recall of these biological neural networks. By the way, the working mechanism of these has already been detected or determined in the 1940s by McCulloch and Pitts. So therefore, this model is also referred to as the McCulloch and Pitts model. So these neurons, they are connected via so-called dendrites. And these dendrites are receptive zones inside the neuron that receive activation from other neurons. Then we have the cell body, which is also referred to as soma. And there, all the incoming impulses are somehow aggregated. And if a specific threshold is surpassed, then the neuron itself fires along its so-called axon a transmission. So the axon is kind of a transmission line that sends activations coming from the cell body to other neurons. And now, this axon connects to other neurons via the so-called synapses. So between the axon and the dendrites of the other neurons, there is a gap. This gap is called synapses, and inside these gaps, an activation is going on the basis of so-called neurotransmitters. And connecting one neuron with another via axon and dendrites, you build up huge or large neural networks. In artificial neural networks, you exactly mirror this kind of configuration. And the very first one and the most simple one is the so-called McCulloch-Pitts neuron, which already has been created in the 1940s, as I already mentioned. So how does this work usually? So there they have the same basic components as biological neurons. How are they built up? So usually in this so-called McCulloch-Pitts neuron, you have a set of inputs that you see here on the left side. These inputs are connected with weights, and there is a threshold bias. And in the end, in the cell body, so in the neuron, all these inputs are weighted and then summed up. And if this sum surpasses a specific threshold, a step function here is activated, and then the neuron fires itself. And here you see the step function. It's here referred to as y sub j, and it's here expressed with the help of a signum function or a sigmoid function, for example, which takes as input the weighted sum of the inputs of the neurons. The bias that you have is quite, let's say, important. This is not only a 1 which is added here with a specific weight to a specific neuron. With help of this bias, what you can do is to assign a specific threshold, or also to learn a specific threshold for each of the neurons that you have in your network. So there is this bias, and this allows usually also bias to be captured from input neurons, as well as it allows a normalization of output thresholds without the loss of generality. So this is the most basic building blocks of these neural networks. Now, starting with this building block, let's set up an artificial neural networks. And using artificial neural networks usually to solve real-world problems, this is a so-called multi-stage process. So let's have a look how this works. First of all, before you apply a neural network, you have to understand your problem and you have to specify, of course, the problem in terms of inputs and required outputs. So what is expected to get into your model and what is expected to come out of it. So this is the first thing you have to do. Next thing, usually you take the simplest form of network that might be able to solve your problem. So for example, take a perceptron or something more complicated, depending on your problem. Then, of course, you try to find out what are the appropriate connection weights and the neuron thresholds so that the network produces appropriate outputs for each input in its training data. This is the so-called learning phase. Usually for that you have its supervised learning, you have a set of training data, and with the help of that training data you try to find the best suiting or the appropriate connection weights and the threshold that your model is able to solve exactly your problem that you have specified under number 1 here. So next you test the network on its training data, and then you test also the network on validation data or test data. And if it doesn't perform well enough, go back to step number 3 and of course try to work harder. If this doesn't help, so if learning is not sufficient, then of course you have to go back further. You go to point number 2 and probably you take a more complicated and let's say a more complex network that might be able to solve your task. And if this even doesn't work, then probably you have wrongly or let's say not completely understood your original problem, and you have to work on the encoding of your specification again and again. Then you have to work harder. In the end, if everything works out well, your problem is solved and you move on to the next problem, which again you will solve in exactly the same order. So this is the basic algorithm how you apply neural networks to your problems. Okay, but yet now let's look at the model itself. Let's look at the most simplest form of the neural network, the so-called perceptron, which was already established in the 1950s. What is a perceptron? The perceptron is an arrangement of a one input layer of activations feeding forward to one output layer of these so-called McCullough-Pitts neurons. And this is a simple perceptron. As you already might assume or see, this kind of perceptron is only able to solve so-called linear problems. It's a linear separator. So if you have, for example, here a scattering of data, it's able to separate this kind of data via a linear function, which is for 2 dimensions a line, which is for many dimensions then a hyperplane. So it's a linear classifier, simply because we don't have many layers, so there is no multiplication or aggregation of different intermediate layer outputs. So therefore it's a linear model. Okay, how does it work nevertheless? So what you do usually if this perceptron should learn, in the learning phase you start by initialize the weights first randomly. Then take a sample x, y and predict yi. So you take a sample and predict the output. And then what you do for your erroneous prediction, so if you do an error, you update the weights. So in case your output was 0 and the desired output should be 1, you have to increase the weight, simply. Or if the output was 1 and the desired output was a 0, you have to decrease the weight. And doing this again and again and again, you repeat this process until no errors are made anymore, and then your perceptron is perfectly adapted. But remember, this is a linear classifier, so it won't end up with 0 error in a case when there is no linear separation possible. So it looks quite easy, but nevertheless, then let's have a look at the mathematics behind it. So first of all, we have to have a look at the network activation function that is happening in each neuron. So here is a rephrase of exactly that function that we have already seen on the slide. So here it's a signum function that works on an input which is the weighted sum of all of its inputs, and then what you do here is you subtract a specific threshold. This is the threshold for exactly that kind of neuron. This is the activation function. And to learn the weight of a neuron for the next step, This is working in the following way. So we have here a weight sub ij, and for the time t plus 1, this is exactly the old weight from the time t plus a delta weight. And the delta weight usually is computed in the following way. What you have here is you apply a so-called learning rate coefficient. The higher it is, the faster usually then is the learning. And you have a desired output. And of course, from the desired output, you subtract the actual output, which of course is your error. And you multiply this with the input. And exactly this is your delta weight that you apply to adapt, to adjust the weight. And it works exactly in the way that we have seen. So if, for example, the actual output was too high, the weight is lowered. If the actual output was too low, the weight is raised. So this is the basic principle, and this is the basic learning algorithm for the perceptron. So here now is the learning algorithm in more detail. We have an input vector you see here, starting with a 1, which is the bias, and then you have all the x sub 1 to x sub n. We have a weight vector, which starts with b, that's the weight of the bias, and then you have w1 to wn. And then you have your actual response. So this is what the network computes, and you have your desired response at time t, everything, which is d of t. And then you have the learning rate that you specify somewhere between 0 and 1. We start with the initialization process. So we set W0 at time 0 to 0. And then we perform the following computations for each time step starting by 1 until the error, let's say, is not anymore changing. So how does this work? First of all, we have the activation phase. So at time step t, what we do is we activate the perceptron by applying continuous valued input vector and desired response. And then we do the computation of the actual response. So we compute y of t with the help of the activation function. And then we simply adapt the weight vector according to the error that is produced, so the difference between the desired output and the actual output. So simply by applying the formula for the weight adaptation that we have seen before. And for example, if you define belonging to a class or not belonging to a class here as the output, you can encode it like, let's say, a +1 or a -1, that it is expected if, let's say, something belongs to a specific class 1 or to another class 2. So this is a way of encoding exactly that. And then you continue, you increase your time step, and you go back to number 2 and you do activation again. And of course, you repeat this until the weight vectors don't change anymore. And then your perceptron is already trained. So what can you do with it? We have heard it's a linear classification model. However well it works, it won't ever be able to mirror, for example, or to produce this simple exclusive OR function. You remember exclusive OR from logic? If you have two inputs, x sub 1 and x sub 2, and you want to determine the exclusive OR, then the output is only 1 if either x1 or x0 is 1. It's 0 if both of them are 0 or both of them are 1. So let's have a look what that means for the weights. If we look at the weights, for example, then you see here what is computed in exactly that small kind of network or perceptron that we have plotted in here with the input x sub 1 and x sub 2 and the output y1. So if the inputs are 0, then of course also the output should be 0, which means our thresholds usually we don't care what they are, so usually they are larger than 0. In the case that one of both is 1, so x1 is 1 or x sub 2 is 1, then you see here the according weight of the input should definitely be larger than the threshold. Otherwise, one could not be computed. But if now both of them are 1, the problem is that the sum of both should be lower than the threshold, because otherwise a 0 could not be computed. And this exactly cannot hold all at once. And simply for that reason, so you can't compute any weight that fulfills exactly these kind of equations, We can visualize exactly this also here in a diagram. You see here a diagram with x sub 1 and x sub 2, and you have here the according dots. And what we want to identify or activate is exactly this one. You see these two dots should be separated from the other two with the help of one straight line. And this, of course, is not possible. So you can't do that with one straight line. Therefore, you see simply a linear classifier is not able to solve the XOR problem. For that, you need a nonlinear classifier. And this also was in the early 60s or mid-60s one of the reasons why the first so-called winter of artificial intelligence began. Simply because people had no idea really how to solve that problem or to cope with these nonlinear networks. But it's quite simple to deal with it. So what you could do to circumvent this limitation of the perceptron is twofold. Either you could use so-called non-monotonic activation functions in your neurons, or you simply add at least one layer in the middle, which is then a so-called hidden layer, with nonlinear activation functions that you already have. So you have exactly the same activation functions, let it be a sigmoid function or a signum function. And then you are able to circumvent this limitation, because then you are already dealing with a so-called quadratic or polynomial classification. The only problem is you cannot apply the original algorithm, since you have no idea what should be the desired output of the neurons in the hidden layer. So the problem then was, it took a while until an algorithm was developed, and this was in 1986 by Rummelhardt, that was able to repropagate the error through the network without definitely knowing what is the expected output or the desired output of these hidden nodes. And this is the so-called backpropagation algorithm, and this is the basic building block or the basic algorithm that works in each of these deep learning networks that have multiple layers. So, in deep learning, we are dealing with so-called multi-layered neural networks, deep neural networks. And the algorithm to learn in these networks is the so-called backpropagation algorithm, which consists of two phases. Now, let's consider a deep neural network with at least one hidden layer. First phase that goes that is working in the backpropagation algorithm is the so-called forward phase. So what are you doing in the forward phase? So the synaptic weights first of the network, they keep fixed, they are fixed. And the input signal is propagated through the network layer by layer until it reaches the output. While, of course, the synaptic weights are fixed. And then the only changes that occur are, of course, then the activation potentials and the outputs. This is the forward phase. So you compute everything starting from the inputs to the output. And now there is a backward phase. What you do then there, of course, in the last layer, you can compare the desired output with the actual output, and you produce a so-called error signal, which is then retransmitted backwards through the net. So the resulting error signal is propagated through the network layer, again layer by layer, in backward direction. And then successive adjustments are made to the synaptic weights of the network. But the mathematics, how to do this exactly, again, this works via a gradient. We let it out here, and if you are interested in it, of course, you can read it up in the material section or in the according paper. But this is only to get an impression how the backpropagation, this two-phase algorithm works. And of course, then it works again and again until the error, which is computed, reaches a specific lower threshold, for example, and then the algorithm stops. Okay, now the next question is how to improve the performance of these networks, of these neural networks. And one important aspect is the features. So, the quality of your machine learning approach always depends on the appropriate assembly of the features that you are using for learning. And this process, where you apply, of course, the domain knowledge to improve or to create the features that you are using for your learning task, this is referred to as so-called feature engineering, and this is really important because usually this is a manual task, and of course you have to know the domain to derive the right features. So usually it's designing manually what the input x sub I should be. And of course, this process is not an easy one. So usually this process is difficult, it's time-consuming, and it requires lots of expert knowledge. But in deep learning, even the phase of feature construction more or less is automated and can be learned. And this, of course, is one of the main qualities, or let's say the benefits that you have if you go for a deep learning algorithm. So deep learning is not only looking at multi-layered perceptrons or multi-layered neural networks, it's also about designing the correct features and learning the features. How does this work? First of all, let's have a look at a deep learning network. So if you look at a deep neural network with more than 1 or 2 hidden layers, so this is a multi-layer neural network, let's assume a task like, for example, image content analysis. And you get an image, let's say, from a contemporary camera, which has several million pixels. And now imagine you have over 1 million inputs. And then you connect, let's say, several layers of 1 million neurons, one with each other. This would be a rather complex network. You already see it here in the example. In the example, we assume hidden layers with 1,000 nodes each, and here you have 2 hidden layers or 3 hidden layers. And the connection between these 3 hidden layers with 1,000 nodes each would cost us about 2 million parameters that have to be optimized between the hidden layers only. And you can imagine that this, of course, is really time-consuming. And if you do it exactly in that way, so if you do it with images where you probably then would require 1 million nodes in there, this again would also completely overfit, because you only would recognize the image if you see it exactly from one direction. So there is no spatial invariance, and this kind of network would lack generalization entirely. So therefore, one came up with ideas how to overcome exactly this problem of no spatial invariance. And therefore, we came up, or the community came up, with so-called convolutional neural networks. These convolutional neural networks are deep neural networks, and they are specifically well suited for the task when you have spatially arranged data, like it comes, for example, with pictures. So CNNs are particularly adapted for, or well adapted for, visual analysis tasks. And the basic building block you have here is the feature learning part. And for this you have different kind of layers which are introduced into the neural networks, or which are then in the pre-processing part of the entirely connected neural network. And this is the feature learning part. And there you have convolution and pooling layers, which do certain filter operations in the convolution layer and then subsampling operations in the pooling layer. And exactly also these layers can be learned. And therefore this combination or aggregation of features somehow is motivated or reflects the way how also in our visual cortex the information processing is working. Before, the information from the eye, for example, hits the brain. So there is the visual cortex where lots of these, again, filtering and pooling operations are carried out. So this is pretty similar to that. So what is convolution? Usually in the convolution layer, what you do is you examine a specific area of your original input field from different perspectives, and you apply a so-called filter kernel. So what you see here, for example, you have a rectangle input, and there you have a small window which is step by step moved over the input, and within this window a specific filter kernel operation is computed. So there is, for example, a specific feature examined, like, for example, they look at the color, they look at the edges, they look at the brightness or something like that. And then, of course, this operation maps the results to then possibly a smaller output convolution layer. And to further reduce the information, subsampling is taking place in these so-called pooling layers, and there usually values again in a window like that are spatially arranged somehow or in spatial neighborhood. They are aggregated, for example, by building an average or by looking for the maximum or something else, or by doing a pooling operation, a subsampling operation. And then, of course, this input pooling layer is mapped to a much smaller output pooling layer. And by looking at the entire network again, you have sequences of consecutive convolutional and pooling layers before the information that comes out of the last pooling or convolution layer hits the fully connected neural network, which then has a much lower dimension. So pooling is also responsible for the dimensionality reduction, which is really, really, let's say, important, especially if you have, let's say, an input of an image which has several million pixels, for example. And then, of course, this is much more efficient. On the other hand, what also is really interesting, you can train your feature learning, for example, on a huge set of data and then simply change the classification layer to a new problem and learn the classification anew, while, of course, keeping the feature learning part in your CNN, in your convolutional neural network. So you can reuse the visual pre-processing, and only then the classification part has to be learned again. And this, of course, makes convolutional networks so popular, since you can reuse many things which have already been developed here. Probably you know these popular applications like that one, where you can adapt an arbitrary picture to the style of a rather famous work of art. So here you have the example, for example, the left one, it's the Starry Night picture of Vincent van Gogh, and the other one, it's The Cry from Munch, that you probably know. And then we have a typical cityscape, a medieval cityscape of a German city, and then you see this picture in the style either of Van Gogh or of Munch, which can be used by a pre-trained neural network that has learned exactly the feature processing or the style of one of these artworks. And of course, what we did for fun is, here you see your teacher in the style of a cave painting. And there are apps that you can download either for your mobile phone, or you can also carry out online here, where you can upload a picture and change it in the style of a pre-trained neural network. This, of course, is not the end of the development of neural networks. There are many developments going on, and the end is not in sight so far. One thing I wanted to show you, which came across to me a few weeks ago, is the so-called Generative Adversarial Networks, GANS. So this is really great. So these kind of networks, it's also a deep learning neural networks, they have been applied to an interesting task where you have to create a picture from a textual description. So what the GAN, or the Generative Adversarial Network, does here is it gets a description like that one. The bird is blue with white and has a very short beak. And then what the network does is not simply looking for a bird like that in a huge database. It simply tries to think of a bird that looks like the description. So it artificially constitutes this kind of picture. And you see here from these depictions that the network creates after several stages that are getting clearer by the stage, that it is really able to think of a bird that has exactly these kind of features, while not recalling an exact picture of that, by just imagining. So it's like in your mind, like your mind also would imagine a blue bird with a short beak, for example. And this, of course, is rather impressive. So now we have reached the end of our lecture of machine learning, and I hope you have gained a bit of an insight in what is going on in machine learning and what are also now the current trends. In the very last part of the lecture, in the last lecture, next week, we will put everything together and you will see some practical work and combining the results we have already learned.